Welcome all for this lecture. Last time we have seen one example how to solve Bode plot, but in that problem, a simple problem we have seen. In that problem we have not seen with any 0 and complex conjugate pole. So, today we will see how to solve with all the possible components in the transfer function, that is zeros, poles, complex conjugate poles and all other things. So, before going towards the solving the problem, once again we will see the semi-log paper. So, all of you know the semi-log paper, but I am explaining it again, that x axis you can see the logarithmic scale, that is it is nonlinear scale. Difference between 1 and 2 is more, 2 and 3 is less than 1 and 2, like that it becomes crowded at 7, 8, 9 there. Then one unit is called decade, because of the logarithmic frequency or the logarithmic scale, we are considering the units as 0.1, next is 1, next is 10, meaning is that the frequency ratio is 10 times. So, 1 unit is called 1 decade. X axis we have to use logarithmic scale, y axis we have to use the linear scale. Usually while drawing the Bode plot, you take at the center x axis and y axis towards the left side, because we want to use the quadrant 1 and 4, and that is why the whole paper should be available for that. Then some people are using that minus 20 dB per decade slope line at one corner. So, that also you can do, otherwise separately I have already explained, and again I will explain in this example how to get the slope with minus 20 dB per decade, minus 40 dB per decade in that way. So, today we will see one example, and the problem is given that draw the Bode plot for the transfer function Gs is equal to 64 into bracket s plus 2, that is 1 0 is there, upon s into bracket s plus 2s s plus 2s s plus 2 and see the problem, s plus 0.5 s and s square plus, so you take the problem properly, s plus 0.5 s plus s square plus 3.2 s plus 64. Plus 64. So, check the problem again, Gs is equal to 64 into bracket s plus 2 upon s into bracket s plus 0.5 s plus s square plus 3.2 s plus 64. So, this is in the pole 0 form. So, what is your first step? First step is rewrite the transfer function in time constant form. And it is in the frequency domain or sinusoidal transfer function. So, what we will get here, g j omega is equal to, replace s by j omega. So, I think I will solve here and then finally write there. So, what we will get, 64 into bracket j omega plus 2, that is replace s by j omega into bracket j omega I think the term s plus 0.5, just s plus 0.5, correct it, j omega plus 0.5, and this is complex conjugate pole now, j omega square plus 3.2 j omega plus 64. So, the first step is replace s by j omega. Next step is we want to convert it in time constant form. So, how will you get it time constant form? Here I want 1 plus j omega t. So, what is the time constant form? We want it as 1 plus j omega t. So, this I want 1. So, if I want this 1, I have to divide here by 2 and then multiply by 2. So, what I will get here is 1 dividing by 2. So, 1 into j 0.5 omega. As I am dividing by 2, I have to multiply here by 2 upon j omega. Here I want 1 plus, so I have to divide here by 0.5 and then multiply by 0.5. So, dividing by 0.5 gives me 1 plus j omega divided by 0.5 means 2 omega. As I am dividing here by 0.5, I have to multiply here by 0.5 into j omega square. I want, so what is the complex conjugate pole formulation which we are considering? It is 1 minus u square plus j twice zeta u, where u is omega upon omega n, that is 1 minus omega upon omega n bracket square plus j twice zeta omega upon omega n. So, I want this as 1. So, I have to divide the whole equation by 64. Okay. So, the whole equation I am dividing by 64. So, I have to divide here by 64 plus 3.2 divided by 64 j omega plus 1, and as I am dividing here by 64, I have to multiply here by 64. So, if I am multiplying here by 64, this 64 will get cancelled with this 64. So, simplify it further now. So, what we will get 0.5 at the denominator and here it is 2 upon 0.5. So, you will get here 4 into 1 plus j 0.5 omega upon j omega into bracket 1 plus j 2 omega. Now, concentrate on this term. Here this is 1 minus, why minus I will get? Because of j square, and then I will write here omega upon 8 bracket square 1 minus u square plus j. So, what is remaining term that we will write here? So, 3.2 divided by 64. So, what you will get here is 0.05. Check it whether it is correct. So, what you will get here is 0.05 omega. I want omega by 8. So, if I want omega by 8, I have to divide here by 8 only. So, what I will get here is 0.4. Okay. So, I will get here 0.4 into omega by 8. Check it, dividing by 64 gives you the value is like this. So, omega by 8 is your u. See, once again what we are doing, replace s by j omega. So, we will get it like this, but we want it in time constant form. So, time constant form means 1 plus j omega t. So, this is j omega plus 2. So, divide here by 2, multiply by 2. Here divide by 0.5, multiply by 0.5. Divide by 64, multiply by 64. And then simplify. So, 64 will get cancelled. 2 divided by 0.5 gives you 4. 1 plus j 0.5 omega, j omega into 1 plus j 2 omega, and here this is 1 minus, because of j square, omega upon 8 square plus j, I want omega by 8. So, 3.2 divided by 8 gives me 0.4. So, what is u here? U you will get is omega by 8. Omega by omega n is your u. So, u is equal to omega by 8, and then you can write it in terms of u. Okay. So, the transfer function which you will get, that I think I will rub all these things and directly I will write here that in the time constant form I will get here the function is 4 into 1 plus j 0.5 omega upon j omega into bracket 1 plus j 2 omega into 1 minus u square plus j 0.4 u, where u is equal to omega by 8. Okay. So, the first point or the first step is see the transfer function given to you and convert it into time constant form and the sinusoidal transfer function. So, you will get the transfer function is in this way. So, the first is rewrite the given transfer function. Second is whatever are the different terms, we will try to represent it in a table. So, form a table. So, which are the columns you will get? First is the factor, serial number you may write or you may not write. So, first is the factor which you are considering. Second is the corner frequency. Then log magnitude plot. And the phase angle plot. See, whenever we are considering the transfer function, then we have to separate the terms, write it in table and then we combine it. See, when I am considering log magnitude plot, I have to take 20 log of all the terms. So, consider now one by one terms. First you consider 4 by j omega. So, k upon j omega term. Corner frequency is nil. Next, corner frequency of this is 2. What is the corner frequency? If I am considering omega t If I am considering 1 plus j omega t term, then omega is equal to 1 by t is my corner frequency. Here 0.5 omega means omega is equal to 1 upon 0.5, that is 2 is the corner frequency. Here 2 omega means omega is equal to 1 by 2 is the corner frequency. So, main thing which you have to remember is arrange these corner frequencies in ascending order, that is important. So, which term you will consider now? Here the corner frequency is 2, here the corner frequency is 0.5. So, 0.5 is less than 2. So, you have to consider the corner frequency, the first corner frequency omega 1 is equal to 0.5. Which is that term? The term is 1 upon 1 plus j 2 omega 1 by t, that is 1 by 2. So, 0.5. So, this is the main thing which you have to remember, that corner frequencies should be in ascending order. Next, consider corner frequency. For this it is 2, for this u is 1, that is omega is 8, that is your corner frequency. So, you have to consider omega 2 is equal to 2, that is 1 plus j 0.5 omega is the next term which you have to consider. And the last remaining term. So, check that 4 upon j omega you have taken, 1 plus j 2 omega that you have taken, 1 plus j 0.5 omega that you have taken. So, what is remaining now? 1 upon 1 minus u square plus j 0.4 u. So, this term we are considering. So, if it is j 0.4 u, what is the value of zeta, where zeta is equal to, see what we are considering, j twice zeta u, j twice zeta u. So, twice zeta u or twice zeta is equal to 0.4, is not it? Twice zeta is equal to 0.4. So, what is zeta? Zeta will be 0.2. So, that you write down, zeta is 0.2. So, the value of zeta, that is damping factor, is 0.2. What is corner frequency here? Corner frequency is u is equal to 1. What is u? Is equal to omega upon omega n, and that is omega by 8. So, omega is equal to 8 is your corner frequency. So, third corner frequency is 8. Okay. Next is log magnitude plot. So, first describe and then draw the Bode plot. So, describe here, what you will get here, 20 log of 4 you find out, 20 log of k. So, 20 log of 4, first find out this value. So, what is it? 20 log of 4, find out it is 12 dB. Then what you will get here? Line passing through 12 dB at omega is equal to 1 with slope. So, write down here, line passing through (12 dB) at omega is equal to 1 and with slope minus 20 dB per decade. I think we have discussed it properly. So, you know, because it is single j omega term, only one j omega term, slope will be minus 20 dB per decade. If it is j omega square, it is minus 40 dB or minus 20 into r if j omega raised to r term is there. What about this? It is pole, real pole, and the corner frequency is 0.5. So, for the omega is less than or equal to 0.5, the magnitude or m is equal to 0 dB, and for omega is greater than 0.5, the magnitude or the magnitude plot has minus 20 dB per decade. Line with or asymptote with minus 20 dB per decade. What about here? Omega is less than or equal to 2, the magnitude is 0 dB. For omega is greater than 2, line width see here it is at the numerator, this is 0. So, what I have to write now? It is plus 20 dB per decade. This is at the denominator, it is for the pole. So, you will get minus 20 dB, this is at the numerator, and so you will get plus 20 dB. That is the difference, one is 0, one is pole, and accordingly you have to change here. What you will write here? For omega is less than or equal to 8, the magnitude is 0 dB, and for omega is greater than 8, line width minus 40 dB per decade, this we have seen as we are getting minus 1 minus u square bracket square. So, u raised to 4. So, you are getting 40 dB, and that we have seen separately. Now, combining all these terms you will get here. So, this is for the asymptotic plot. For the asymptotic plot you will get it like this. This is log magnitude plot. What is phase angle plot? So, at omega 1 is equal, see here it is constant k will not contribute any phase angle, 1 upon j omega gives you constant minus 90 degrees angle. For this term it is 1 upon 1 plus j omega t. So, at omega 1 is equal to 0.5, phase angle will be 45 degrees, minus 45 degrees, it is pole. So, it is minus 45 degrees. As omega 1 tends towards infinity, phase angle tends towards minus 90 degrees. Here at omega 2 is equal to 2, phase angle is plus 45 degrees, because this is at the numerator term, and as omega tends to infinity, phase angle will tend towards plus 90 degrees. For the last term we will get at omega is equal to omega 3, the phase angle will be minus 90 degrees. As omega is tending towards infinity, phase angle will tend towards minus 180 degrees. So, this is asymptotic plot, approximate plot. So, first on paper you have to create a table. So, once it is possible to create a table, then you can draw it on the graph paper. So, how will you do this? Now, I will use this side for drawing the graph. So, as I have told already you take at the left hand side your y axis and at the center x axis. X axis is your omega logarithmic scale. So, if this is 0.1, see whether 0.1 is sufficient or you want lower than that you observe here the corner frequencies. So, here the lowest corner frequency is 0.5. So, 0.1 is sufficient. Suppose your lowest corner frequency is less than 0.1, then you have to take this 0.01 as your starting point. Or here also you can take 0.01, no problem. Then next is 1, next is 10, next is 100. That is 1 unit we are representing as the frequency ratio 10. See 1 upon 0.1 frequency ratio is 10, 10 upon 1 frequency ratio is 10, 100 upon 10 frequency ratio is 10. So, 1 unit is called 1 decade, frequency ratio is 10. On y axis scale is linear, you take it as 10 dB, 20 dB, 30, so like that all in dB. Similarly, here minus 10, minus 20, minus 30 in that way. Okay. Now, whatever you have described in the table, that we will try to draw it on the semi-log paper. So, what is the first term? 20 log of 4 is equal to 12 dB and at omega is equal to 1 it is 12 dB. So, suppose this is 12 dB, then at omega is equal to 1 it is 12 dB. 20 log of 4 is 12 dB, at omega is equal to 1 you will get now 12 dB. On graph paper you draw it properly, as I am drawing here it is not to the scale. Then line passing through this point with minus 20 dB per decade you have to draw for this factor. So, how will you draw a 20 dB per decade slope line? This is 12 dB. Within 1 unit I want 20 dB difference. So, what I have to consider the point on here 12 plus 20. So, what is it? 12 plus 20, that is 32. So, you take the point 32 here and draw a line which gives you the slope of the line as minus 20 dB per decade. So, the slope of this line is minus 20 dB per decade. See whether whatever is described in the table and you have drawn it. What we have described here, 20 log of 4 is 12 dB, that first we have to calculate. Then line passing through 12 dB at omega is equal to 1, that is at omega is equal to 1 it is 12 dB and slope of the line is minus 20 dB per decade. Meaning is that within 1 decade change is 20 dB. So, what I am considering at 0.1 it is 32, at 1 it is 12, meaning is within 1 decade slope is 20 dB, okay, minus 20 dB, it is decreasing, and the first factor Bode plot is over. Consider second, 1 upon 1 plus j to omega, corner frequency is 0.5. So, this is 0.1, somewhere here you will get 0.2, 0.3, 0.4. So, I will represent, see this is non-linear scale. So, you will not get exactly at the center, but it is towards 1 you will get, suppose this is 0.5. You draw on your graph paper, properly represent. On the graph paper it is written 1, 2, 3, 4, 5 in that way, but when you are considering 0.1 to 1, 5 represents 0.5. So, what is description? For omega is less than or equal to 0.5, magnitude is 0 dB, meaning is till here the magnitude is 0 dB. For omega is greater than 0.5, line width minus 20 dB per decade. So, this is the line width minus 20 dB per decade. you can draw a parallel line to this. Otherwise, what you can consider, at 0.5 it is 0, then take a point where it is 5. So, suppose here it is 5, then at 5 it is minus 20 dB. At 5 it is minus 20. So, again within 0.5 to 5 is 1 decade, frequency ratio is 10. In that decade, change in dB is minus 20 dB. So, the slope of the line is minus 20 dB per decade. But it is better if you have one line with slope minus 20 dB per decade, draw a parallel line. So, that will be easy for you while drawing it. So, this you will get a parallel line to this, and so the slope of this line is again minus 20 dB per decade. So, the second factor is over. Consider third factor, 1 plus j 0.5 omega, corner frequency is 2. What is description? For omega is less than or equal to corner frequency 2, it is 0 dB. See why ascending order is required, that is clear here. Till omega is equal to 2, contribution of this factor is 0 dB, and so you have to write it in ascending order. So, suppose here it is 2, this is your corner frequency. So, till 2 it is 0 dB. Then plus 20 dB per decade for the frequencies greater than 2. So, this is 2. 1 decade means you consider the frequency where it is 20. So, this is 1 decade. Within 1 decade, the change is plus 20 dB. So, plus 20 dB here, and you draw the line. So, you take the proper scale and draw properly. Okay. So, what is the slope of this line? Slope of this line is plus 20 dB per decade. Why plus 20 dB? Because within 1 decade, change in dB is plus 20 dB. How will you draw the line? If I have the corner frequency 2, take next decade, that is 10 times that. So, it is 20. At 20, you want plus 20 and then connect these two lines. So, you will get for the third factor. Now, for the last factor, at omega 3 is equal to 8, or for till that you will get 0 dB. So, suppose 8 is here, till that the contribution of this factor is 0 dB. When frequency is greater than 8, line with minus 40 dB per decade you want. So, how will you take the line with minus 40 dB per decade? At 8, it is 0 dB. So, take a point 80. So, you will get now here 1 decade. At 80, it is minus 40 dB. So, see here, as per your scale, this is minus 40. So, at 80, you will get minus 40. Okay. So, draw a line this. So, the slope of the line is different than minus 20 dB per decade, and this is minus 40 dB per decade. Why? Because this is 8, I am taking 1 decade, that is 80, and within that 40 dB change. So, minus 40 you can draw a line. Is it okay? So, you will get minus 20 dB, plus 20 dB, minus 40 dB lines for these 3 factors, and here no corner frequency, line passing through 1, at 1 it is 20 log of k. So, this is approximate plot. Now, we will try to combine all this. Okay. So, how will you do this combination? Say first corner frequency is your 0.5. So, till 0.5 which factor is contributing? Only this. Till 0.5 contribution is only because of 4 upon j omega. So, till 0.5 the contribution is because of this only. So, combination or the combining we will get it this one. After 0.5 the contribution is because of this plus this, that is because of this factor 4 upon j omega as well as because of 1 upon 1 plus j 2 omega. So, what we will get? Because of 4 upon j omega it is minus 20 dB per decade, and because of 1 upon 1 plus j 2 omega it is minus 20. So, what you will get? Minus 20 additional minus 20. So, minus 40 dB. How will you draw the minus 40 dB line? If you have now the line with minus 40 dB, you draw a parallel line. Otherwise, you have to observe what is the value at 0.5 you are getting. Take one decade and make a minus 40 dB within that. As you have minus 40 dB per decade line, take the same slope, okay, and draw a line. Okay. So, draw a line. So, I am considering approximately where it is crossing on the x axis. Okay. So, from here I will get, so till the next factor it will because of these two factors. So, next is omega is equal to 2. So, till omega is equal to 2 the contribution is because of this and this. So, here also you write down this is minus 20 dB per decade. Now, this is minus 40 dB per decade. So, till 2 it is because of the contribution of these two factors. What will happen after 2? After 2 third factor will contribute, because till 2 contribution is 0 dB. Now, when omega is greater than 2, line with plus 20 dB per decade we have to draw. So, till 2 whatever point you will get here, this is the line with minus 20 dB per decade. So, draw a line parallel to this till 8. So, till 8 you draw a line parallel to minus 20 dB per decade. Why now this is minus 20? Already it is minus 40 dB per decade. This factor will contribute plus 20 dB. So, minus 40 plus 20. So, how much we will get? Minus 20. So, this is the minus 40 dB per decade scale till 2. After 2, this factor will contribute plus 20 dB per decade. So, the slope of the line will change from minus 40 dB per decade to minus 20 dB per decade. So, this is with minus 20 dB per decade, because this factor will contribute now. So, the slope of the line will change. This line parallel to minus 20 dB you can draw here till 8, because next corner frequency is 8. From 8 this factor will contribute. What is its contribution? Till 8 it is 0 dB. So, that we have considered. For omega is greater than 8, it will contribute minus 40 dB per decade. Okay. So, minus 40 minus 20. So, how much you will get? Minus 60 dB per decade. How will you draw that line? Within 1 decade, I want minus 60 dB. So, if I have not considered the scale till minus 60 dB, what I have to do? You can consider the line above also. So, total this 20, this 40, 60 dB scale within 1 decade you should get. Okay. So, the slope of the line is like this, and considering that you draw a line from this with the slope as minus 60 dB per decade. How will you take it, the slope? So, take it properly, that is 8 to 80 you want 60 dB. So, for 60 dB what you can take is you take this 20, this 40, so total 60 and draw a parallel line to that. Okay. So, I am approximately drawing, you draw it perfectly. Minus 60 dB per decade line. Why minus 60 dB? Because already because of these 3 terms you are getting minus 20 dB per decade. This will contribute additionally minus 40 dB. So, minus 60 dB per decade, and so you draw a line with minus 60 dB per decade. Okay. So, this is the asymptotic plot, that is approximate plot. You have to do the corrections. How will you do the corrections? We have seen that at corner frequency maximum error is there. So, you have to use that and do the corrections. So, I will rub this because there is no space, and this part is over now, only phase angle. Okay. So, I will rub this. So, asymptotic plot, asymptotic magnitude plot is over. For the phase plot, what you can do? You can draw the separately for each term, that is represent now on the same graph paper y axis in terms of angle. So, what you will get here, if I am representing with the angle, this is 0, this is minus 45, this is minus 90, this is minus 180. Okay. As per this, at omega is equal to 1, it is minus 45 and minus 90. So, how will you get it? Tan inverse function, and so the plot will be like this. It is not, it will not connect to the minus 90, but it will go towards minus 90. This is for the factor this. For this factor minus 90 constant. For this factor, it is at corner frequency plus 45. So, here it is minus 45, you make it plus 45 plus 90 in that way. So, what you will get at 2, it is plus 45. And how will you get variation? As plus tan inverse function, and it will go towards minus 90 degrees, towards plus 90 degrees, but it will not reach the 90 degrees. So, this is because of this factor. What about this? When omega 3 is 8, it is minus 90 degree. Okay. And tan inverse function approximately with zeta is equal to, what is the value? 0.2. You have to draw, but approximately first we will draw. So, at 80 it is 90, and you will get here the plot tan inverse function. So, at 80, at 8 it is 90, and as you going away it will go towards minus 180. So, these are approximate plots, and what you have to do? Algebraically add together. So, here I will consider that this will get cancelled with this is additionally. So, minus 90 plus somewhere here I will get the plot, I will get the point. Take similarly at 0.5 you will get this, here this is more negative as compared to this, then this is negative. So, you will get more negative term. So, actually you add here whatever are the values you are getting on the graph paper, those you add here. Additionally you will get here. So, considering that you may get your phase plot somewhat like this. So, as it is going minus 180 and minus 90. So, it will cross minus 180 and it will go somewhere here. So, this is your minus 180 line. So, this is your phase plot. This is again asymptotic plot. This is your magnitude plot. Now, you have to do the corrections. So, two things we will see now here. So, I will rub this part. So, approximate plot, asymptotic plots we have drawn. Now, the asymptotic plot you have to correct it. So, we will see the third thing is correction. Okay. So, again make a table for the correction. For correction you make a table. So, what is your table or the which things you will consider in the table? The various corner frequencies and one octave above and one octave below, those frequencies you consider. So, frequency and error, frequency and error. Okay. So, first you consider here the frequency where you are getting the first corner here at 0.5. So, consider the frequency 0.5 and corner frequency, it is at the denominator term or it is a pole. So, how much error you will get? Minus 3 dB. So, that we have seen error correction. So, you will get at 0.5 it is minus 3 dB. One octave above and one octave below you will get minus 1 dB. Octave means half the frequency and double the frequency. Half the frequency means you consider 0.25 you will get minus 1 dB and here at 1 it is minus 1 dB. Okay. So, due to the term 1 plus j2 omega you will get correction like this. At corner frequency it is minus 3 dB, half the frequency minus 1 dB, double the frequency minus 1 dB. What is your next corner frequency? Next corner frequency is 2. What is the error you will get? See, 2 is the term which is at the numerator. So, what is the error you will get here? Plus 3 dB error you will get at the corner frequency. Then you take half the frequency and double the frequency. So, half the frequency is 1. How much error you will get because of this factor? This is at the numerator plus 3 dB and you will get plus 1 dB. So, you add just here that this minus 1 dB error is because of this factor, plus 1 dB error is because of this factor. Okay. Then at 4 it is plus 1 dB. half the frequency and double the frequency 1 dB, at corner frequency it is 3 dB. Whether it is plus or minus will depend on the whether the term is at the numerator or denominator. Okay. Next corner frequency is your 8. So, again similarly you take 8 and 16, double the frequency. Now, here the error is different. So, what is your error? You have to consider the damping factor also. So, with considering the term, we have considered the error. What is the formula we have seen is what formula we have seen here for the error? It is minus 10 log of 1 minus u square plus 4 zeta square u square is the actual value, and we are considering till that it is 0 dB, okay, or 40, and after that 40 log of u, which we are considering. So, minus minus plus you have to consider. So, at u is equal to 1, you will get here the value is 4 zeta square, and accordingly you have to find out, substitute zeta is 0.2, substitute zeta is 0.2 and calculate it. So, find out at 1, u is equal to 1, how much error you will get. So, at for 0.2, as per the graph which we have seen already, it is plus 10 dB. Here for zeta is equal to 2, this is important. This we are considering with zeta is equal to 0.2. So, for 0.2 zeta, this is plus 10 dB. Then at half of the frequency and double the frequency, substitute the value of zeta and find out. So, what we will get is so approximately I am drawing, you find out it perfectly. So, you may get somewhat like this 4 dB or 3 dB like that. So, we will consider plus 3 dB and here it is plus 3 dB. So, this term is approximate. You would substitute the value here, u is half and double you are considering. So, consider double for the half, any one you can consider, this is for the upper range. So, consider double, that is u is 2, okay, and find out what is the actual error. This is the formula for the error. We have seen it in the previous lecture. Okay. So, this is I am approximately taking, you substitute the value and find out it. Now, how will you correct it? See, this is the table which I got it. How I have done this? Take all the corner frequencies. So, which are the corner frequencies? 0.1, 0.5 to 8. These are the 3 corner frequencies. Half of that and double of that I want. So, 0.5 half of that is 0.25 and double is 1. For 2 half is 1, double is 4. For 8 half is 4, double is 16. For that you write the actual values, error and correct it. So, how much correction you will get? At 0.25 it is minus 1 dB. So, this is 0.5. So, you may get somewhere here 0.2, 0.3 and suppose I am considering here is the 0.25. Whatever is that you have drawn, minus 1 dB to that. So, whatever is your value, you take the point minus 1 dB here. As per your scale, you represent that point. Okay. At 0.5 it is minus 3 dB. So, at 0.5 it is minus 3 dB. So, whatever is your value, take minus 3 dB point. At at 1 minus 1 dB plus 1 dB. So, 0 dB, there is no correction. No correction means at 1 whatever is your value is correct, there is no correction required. At 2 it is plus 3 dB. So, at 2 it is plus 3 dB, this is your plot, asymptotic plot. So, this is actual value, you make plus 3 dB point here. Plus 3 dB means whatever value you are getting, add 3 and represent here. Here I am considering 3 dB, considering this 3 plus 1 4. So, at 4 it is plus 4 dB. So, this is your line. So, at 4 you will get somewhere here 4 dB. So, what is this is actual value, suppose this is 4. So, at 4 this is actual value, this is corrected. Then at 8 it is plus 10 dB. So, at 8 this is your value plus 8. So, whatever is this you are getting plus 10. So, this is I think minus 18 I am getting here, then plus 8 plus 10 dB. So, this will be the point. And then here at 16 again plus 3 dB. So, at 16 again whatever is your value you are getting, make it plus 1. So, these are the corrections. And now, what is your actual Bode plot? Magnitude plot. Actual magnitude plot will be, this is the correction. So, start from here, this is your corrected point, this is your corrected point. At 1 you have to join this. So, draw a smooth curve now, okay. Then you have to connect this, next you have to connect this. So, draw a smooth curve, next you have to connect this, and then, so this peak you will get, and from that peak then it will, you connect it to the asymptote. So, whatever is the red line is your actual magnitude plot. So, this is contribution due to all factors as well as correction we are considering. So, correction is standard one that we have decided already. So, what is the standard one? At corner frequency it is minus 3 dB if it is pole, plus 3 dB if it is 0, or the term is at the numerator and denominator. Minus 1 dB for the half of the frequency and double the frequency, plus 1 dB for half and if it is at the numerator. Only the thing you have to take care if it is complex conjugate pole or 0, whatever it is. So, you are getting here the peak that already we have seen how error you are getting, and you will get the error. So, whatever is the plot, this is the actual magnitude plot. Now, while drawing the phase plot, what we have seen, separately you draw each term, this, and as well as whatever the 4 terms are there. So, for 4 terms you will get 4 values and then you connect it. But what is the problem you will get here? That all the plots we are drawing approximately 1, 2, 3 and 4, but all plots we are drawing approximately. So, it is better instead of drawing separately for each term, you make again a table for the phase plot, find out the values and directly represent that angle at that frequency. So, once you will get 7 to 8 points, draw a smooth curve, that is your phase plot. So, that will save your time while drawing the Bode plot. So, what you have to do, which frequencies you will take? Now, these frequencies you have already taken for the error, extend this table for the phase angle. Extend this table or you draw another table, I think it is better to draw another table, but use the same frequencies. so that it will be easy for you, because already you have mentioned those frequencies on your graph paper. So, your fourth step will be for the phase plot. So, fourth step for the phase plot, okay. For the phase plot, take the frequency. What are the terms that you write here? Okay. So, what is your first term? First term k upon j omega. So, what is here? It is 4 upon j omega. Second term is 1 upon 1 plus j 2 omega. Third term is 1 plus j 0.5 omega, and last term is 1 upon 1 minus u square plus j 0.4 u. So, these 4 terms are there. What is angle contribution by due to this? It is minus 90 degree throughout, constant. That line we have drawn, minus 90 degree constant. So, that line we have drawn. Next is 1 upon 1 plus j 2 omega. What is contribution of this? Minus tan inverse of 2 omega. Angle phase because of this term is minus tan inverse of 2 omega. What is angle due to this term? Plus tan inverse of 0.5 omega. And what is angle due to this? Minus tan inverse of twice zeta u upon 1 minus u square, imaginary part upon real part. So, everywhere we are doing it imaginary part upon real part. So, we will get it like this, and the last column will be, you write here the phase angle phi. Okay. So, what we are doing now? For the point 25 or for complete this row, it contributes minus 90 constant. So, you write here minus 90, minus 90, this is constant. So, no problem for this. Here minus tan inverse of 2 omega. So, at omega is equal to 0.5, you are getting minus 45, that we have done. Now, actually substitute omega is 0.25. So, what you will get there? 0.5, 2 times. So, tan inverse of 0.5. So, substitute that value. So, then tan inverse of 2. So, substitute omega is equal to this value and calculate the angles. Similarly, when you are considering, so you approximately I am considering here, you may get minus 30 degrees. It is not correct, like that you will get, while this will increase in that. So, I am considering approximately. So, I am writing here suppose 56 degrees. So, actually you substitute here tan inverse of 2 times 0.25, that is 0.5, tan inverse of 2, tan inverse of 4, tan inverse of 8, tan inverse of 16, tan inverse of 32, calculate these angles. Similarly, here tan inverse of 0.5 omega, that is at 2, you will get plus 45. Okay? And substitute here. So, what you will get here? Some plus 30 degrees, plus 20 degrees, just approximately I am writing. Okay? And similarly here you will get. and for this considering 0.4 u. So, u is 8, at that time you will get minus 90 degree, and before that whatever is actual angle, substituting u means now omega upon 8. So, 0.25 divided by 8 you take it. So, that is properly you have to consider u is equal to omega upon 8, and this is the value for omega. Okay. So, at 8 u is equal to 1, you will get minus 90 degrees, and all other values you calculate. Now, what you can do? Algebraically sum all this, add it together. So, this gives you minus 90 degrees, this gives you minus 30 approximately I am considering. So, minus 120, this gives you some additional plus thing, suppose plus 10. Okay. So, minus 120 plus 10, that is minus 110, and this will give you some value. So, you add it together and you will get some value minus 100 for example, or for approximation just I am considering. So, add this plus this plus this plus this is the value. So, what you can do? At 0.25 angle is minus 100. So, at 0.25 angle is minus 100. So, like that you will get 1, 2, 3, 4, 5, 6, 7. 7 points are there, 7 frequencies are there. So, for those 7 frequencies you find out exact value for the phase angle. So, 7 points are in your hand, you draw a smooth curve for that is your phase plot. So, it will save your time, because you are drawing for each factor 1, 2, 3, 4 approximate plots, and then at different frequencies you are adding, and then this is your phase plot. Better to make a table, exact values you will get for the phase angle, those you represent here, that gives you phase plot. So, first step is draw asymptotic magnitude plot, then use the correction table and correct it, draw a smooth curve, that is your actual magnitude plot. For the phase plot, you take various frequencies, take all the factors, find out actual contribution of angle due to that factor and add it together, which gives you total phase angle at that frequency. Take 7 to 8 points and draw a smooth curve, that will give you the phase plot. Okay. So, we have seen in this example both things two things additional compared to the last one, that is one is 0 and one is complex conjugate pole. What will happen if complex conjugate 0 is there? Only the term is at the numerator. So, whatever we are considering as because of at the denominator minus term, you will get plus term. Next thing we have to see is stability in frequency domain. Nyquist stability criteria is there, which explains the frequency stability or stability in frequency domain. Now, we will apply that Nyquist stability criteria to the Bode plot and will decide what is the or how to find whether the system is stable or not. Okay. So, for that we have to find out. So, I will rub all this part. So, next thing is we have to decide here stability. For the stability, we have to find out phase margin and gain margin. And to find phase margin and gain margin, we have to find out phase crossover frequency and gain crossover frequency. So, instead of defining it in words, I will try to explain directly on the Bode plot. So, what is the phase crossover frequency? So, phase crossover frequency is the frequency at which the Bode plot crosses minus 180 degrees line, minus 180 degrees line. So, which is your phase crossover frequency? You will get somewhere here is your phase crossover frequency. So, this is your phase crossover frequency. So, as per the definition, so I am not defining it in words, I am just showing it on the graph paper. Phase crossover frequency is the frequency at which the angle is minus 180 degree, that is it crosses minus 180 degree line. So, observing this, if this is minus 180 degree, this is your phase crossover frequency. What is gain crossover frequency? Gain crossover frequency is when the magnitude plot, so this is for the phase crossover frequency, for the gain crossover frequency 0 dB line, when the magnitude plot crosses the 0 dB line, it is called the gain crossover frequency. So, this is your gain crossover frequency. See, this is my magnitude plot, it is crossing 0 dB line at this frequency. So, whatever is this frequency, it is called gain crossover frequency. This is phase plot, it is crossing minus 180 degree line at this particular frequency, whatever is the frequency, that is called phase crossover frequency. So, I think these two terms are clear, gain crossover frequency and phase crossover frequency. So, when gain is 0 dB, whatever is the frequency, that is called gain crossover frequency. So, magnitude plot crosses that 0 dB line, while phase crossover, phase plot crosses minus 180 degree, and that is called phase crossover frequency. Why these two frequencies are required? This is to decide the phase margin and gain margin. So, whenever we are considering, so we will go back again, which is the thing 1 plus GSHS or Gj, we will write Gj omega Hj omega 1 plus GSHS is equal to 0 is your characteristic equation, replacing S by j omega, we can write it like this. So, what is required now? Gj omega Hj omega, we want it minus 1. So, minus 1 we are representing as magnitude and phase, that you want magnitude as 1 and phase is minus 180 degrees, isn't it? We have seen these two things. So, when magnitude is 1, what is in dB? 20 log of 1. So, it is 0 dB, meaning is when the magnitude is 0 dB, means it is 1. So, that point is of importance. Second is phase is minus 180 degree. So, that phase we are considering. Now, this is the point on the verge of instability, that is if this point is touched, it is on the verge of instability. So, what is required is that find out the phase margin and gain margin and decide whether the system is stable or not. So, at gain crossover frequency, okay, you extend this line to the phase plot. So, what we are considering, you extend this or whatever is this frequency, at this frequency you find out what is the phase angle. Okay. At gain crossover frequency, what is the phase that you find out? That minus 180 is your phase margin. So, this is your phase margin. So, phase margin is represented as phase at gain crossover frequency So, I think gain crossover frequency we will represent as omega Gc, phase at gain crossover frequency minus 180 degrees, while gain margin is gain at phase crossover frequency. So, that is omega Pc. Okay. So, 0 dB minus gain at omega Pc. So, this is the actual values how to calculate it. So, extend this line, that is at this frequency what is the phase minus 180. So, this is the difference, this is positive phase margin. See here you will get positive phase margin because this omega phase at omega Gc is less than minus 180. So, plus 180 minus some term that you will get plus positive, and here what you will get, extend this phase crossover frequency to the magnitude plot. So, somewhere here if it is crossing, this is your gain margin. Now, this gain margin something value you are getting minus 10 or some minus 12 something like that. So, 0 minus 12 that is plus, and if the gain margin and phase margin are positive, system is stable. System is stable. So, we are applying here the Nyquist stability criteria, and the point which is of importance is magnitude 1 and phase minus 180. So, these frequencies are first calculated, that is called the gain crossover frequency and phase crossover frequency. Whatever is the phase at the gain crossover frequency minus 180. So, whatever you are getting, this is positive phase margin. Here whatever you are getting is the positive gain margin. So, the system is stable. So, you have to find out what is gain margin, what is phase margin. If both are positive, then your system is stable. Okay. So, with this we will stop here, and the Bode plot module is over here.